I'm going to be talking today about simulation, in particular microsimulation, in the context of a tool that my group has developed called Vivarium. And I'm going to use modeling of potato growth as an example, because I really like potatoes. You may not all agree, but I think they're fascinating. So I'm going to lead in a little bit with general simulation stuff. I'm going to talk some about public health modeling, because that's actually what this toolkit is designed for. So I won't get to potatoes until about halfway through. So if you really don't want to hear about sick people, you can tune out. Okay, so just a brief introduction about who I am. I'm a software engineer from the industry side. Most of my background's in webby startups. Just recently, I started doing academic work, not as an academician, but as an engineer supporting researchers. I work for these guys, the Institute of Health Metrics and Evaluation, which is based out of the University of Washington in Seattle. And we study population health. So this is what makes people sick and how we can make them better all over the world. In particular, my group studies cost effectiveness. So we want to know what's the best way you can spend development dollars if you want to help a population somewhere be healthier. And we do that with simulation tools, among other things. Before we do that, if you're interested, the code that model in this talk, but what I'm going to talk about is available up here. And I was fiddling with it up until like midnight last night, so it probably works, but if you want to take a look, it's there. This is our tool, and that's the actual important part. So please take a look at those if you're at all interested. So why simulation? There's a lot of ways of studying stuff, and we just heard a bunch of things about how you can do science with Python. This is just one way of doing that. So if you have a thing like this, what's going to happen here, right? You shoot a dude out of a cannon. We have a pretty good understanding of that. He's going to follow a ballistic trajectory. You know where he's going to land if he misses his friend acrobat up there, more or less. And you can write an equation for it. It's real simple. And that ignores a lot of complicated stuff, wind resistance, all that. But for the most part, you can describe this system if you know a little bit about the cannon, a little bit about the dude, pretty well. And that's all you need if all you want to talk about is cannonballs. And what happens if you do this? That is a lot more complicated, right? I mean, even if you simplify it way down and you imagine the guy is a cannonball and the other acrobats are, say, a stack of bricks, this is still super complicated. You can't write one equation for this anymore if you want to know where the cannonball stops, right? Or how the bricks fall. And so if you want to study this, you have to look at the underlying mechanisms. You have to do a little bit of physics modeling. You have to do maybe some ragdoll stuff with the figures if you really want them to be acrobats and not cannonballs. But if you do that, if you do some hard body physics and some basic friction and all of that, you can come up with an approximation of what happens when the guy hits the stack of acrobats. And so that's a situation in which you'd want to use simulation. It's where you know something about the underlying mechanisms of the thing that you're trying to study, but you don't have a really crisp way of writing it down in a super easy to analyze form. So you don't have a good simplification, but you have maybe a whole bunch of simplifications of the underlying system that you can sort of tack together to make a model. So that's a situation in which you'd want to use simulation. Lots of other ways of doing this, statistical modeling, but simulation is one approach. So why microsimulation? Microsimulation is special because it talks about systems that consist of many individuals together. So in particular, population health, where you have lots of people. In health modeling and often things like agricultural modeling, you're talking about populations together. And so if you've ever seen any epidemiology, you're probably familiar with this as the SIR model. Stands for susceptible, infected, recovered, or removed. And this is a very, very old model, I think more than 100 years now, of how diseases work in populations. So if you say, 99% of the people in the population are susceptible, some remainder of them are infected, and some remainder of them are already immune, then you can use this model to talk about how an epidemic spreads through that population. But you're talking about proportions of the population, or numbers of people who are sick, not individual people who are sick. You're talking about the population as a whole. So this is population-level modeling, not microsimulations. But it's nice. You can write some equations. These are no longer quite as simple as our cannonball equation. It's a family of differential equations. You have to do some complicated things to make those work out. But you can still do some analysis on it and come up with amazing results. So if you make it a little more complicated, say I've got a disease where I have asymptomatic people, mildly sick people, and really sick people, it starts to get a little more complicated looking. Because I need a bubble in my diagram for every state that someone could possibly be in, whether they're susceptible or sick in one way or sick in another way. If I want to model two diseases together, comorbidity, then I need a lot more states. I need the state where they're susceptible to both diseases, the state where they're susceptible to one disease and infected in one way with the other disease, and another way with the other disease, and another way with the other disease, and recovered with the other disease. So there's a combinatorial explosion here. It gets really, really big, and you have a lot of states. And they start to look kind of like this. This is a relatively simple model that one of my bosses did for a previous publication, Marsha Weaver, for studying influenza vaccinations in populations. It's a lot more complicated. This is still totally manageable. You can get much larger than this, and the computers are fine. Humans start to have trouble thinking about them. And so this is one of the ways in which population-level models like this kind of component models, what these are called, break down very quickly. But if you start thinking about individuals, you can do some interesting things. And so now I've changed my notation a little bit because I'm now talking about a single person, not a population. And this single person is currently alive. That's what the black dot means. They are currently susceptible to one type of flu, like say this year's variety of H1N1, and they're currently susceptible to this year's variety of H3N2, another kind of flu. So I've got the same kind of state space, right? Like if you tried to draw this out as the population level component model, you could. It would be fairly large. But now I'm talking about these things as if they're completely independent models, and that's a pretty good simplification. So I can say, this guy's now sick with one type of flu, but he's not with the other. And as a human, this is still really easy for me to think about, which is nice. And I get that because I get to talk about single individuals rather than trying to model all the possible populations within a given state. But I've missed some of the relationships between things, right? So I know that someone who's sick with the flu is a little bit more likely to die than someone who's not sick with the flu, right? So it's going to affect the rate at which they die. By square boxes represent transitions between states. And so I need some way of representing these things. So you start to get back into some complexity here, because the models are not, in fact, completely independent. But still pretty easy to think about. I can draw that. I can start to make it more complicated. What if I want to model immunosuppression and its effect on making people more likely to get sick? And I can draw these out. Start looking like this. This is an actual model built with Vivarium and Vivarium Public Health, which is a not yet open source, but soon to be open source extension of Vivarium. That my group actually works on. It's a model of childhood diarrhea as a symptom of 13 underlying causes of diarrhea. I'm not going to go through all the details here because there's a lot of stuff going on, but you can see some of the basic concepts here. I have states for any individual disease, a representation of how those affect the symptom, whether or not they're alive, and some relationships between those things. So now you're starting to see how this kind of modeling approaches problems, and in particular how the approach that we take towards problems is. I'm going to break these guys down into chunks, into individual small models that are manageable and as independent as I can make them, and then explicitly represent the relationships between those. So what's Vivarium? Vivarium is a set of tools for doing all of that stuff. It's Python framework. We target Python 3.6, if that matters to anyone. And it sits on top of all of the stuff we just heard about in the keynote. We're using NumPy, we're using Pandas in particular, those two, and SciPy in some places. And so we use the standard numerical or scientific tools for Python. We're relatively low on dependencies, like it's basically just those. And we try and take those things and turn them into tools that you can use to express the kinds of models that I've been describing. So now we're talking about potatoes, because they're the best. This is what I'm going to try and build. So this is a relatively complicated model. If you're used to looking at the kinds of models that people have used to describe these problems, this is not as complicated as they get by a long stretch, but it's fairly sophisticated. To be clear, this is a toy model. The data I'm using to drive it is data that I made up mostly last night. So it's not going to be realistic results, but it's structurally appealing. It's about the right shape that you would want a model like this to be. So I'm going to talk about how I've designed the model, and I'll show you some code of how it's actually implemented in our tool set. But you can see here, I've approaching it in the way that I talked about earlier. I've broken it down into several small models that each talk about a component of the system in as much isolation, as decoupled as possible from the rest of the system. And the decoupling is one of the key concepts that we have in Vivarium, because we want something like this guy, which I have implemented as basically random placement. So this is like if you tipped over a dump truck full of potatoes in a field, this is how they would happen. And the only parameter I have there is a density measure, how on average, how close together are the plants. No one plants potatoes that way, right? But it's a useful simplification. In this model, the only relationship that this has to the rest of the system is XY coordinates for the plants, basically. So I can pull that guy out and replace it with a more sophisticated model where I'm planting in rows or other ways of organizing plants in a field without changing any of these, because they don't care how the plants are planted, they only care where they are. So that this is this concept of encapsulation and decoupling, which, you know, all of you are programmers to some extent, you'll be familiar with that. It's something that is a little bit rare in scientific code. Often they tend to be fairly monolithic and tightly bound. So this is something we're really, really trying to get with this. Yeah, so that's the structure there. So this is it. This is Vivarium. And it's kind of a joke, but it's not really. It's like you set up some stuff, and then you tick a clock forward until you run out of time, and then you write out some results. You know, we have a lot of code to do that, but this is what it does. And this is important, and if you've done any simulation, you'll be wondering about this already, because this tells you the kind of model we are. We are a discrete time model, which means that we have a clock, and it moves forward by fixed time steps. In this particular model, 1 day at a time. You would choose those carefully depending on your model. If I'm modeling something slow moving like heart disease in a population, I'd move forward faster, so like a month at a time or 3 months at a time. Potatoes grow relatively quickly, so I'd move forward a day at a time. And at every time step, we reevaluate the state of the model to determine what changed in the previous, over the course of that time step. That tells you something very important about how our model is structured. There's other ways of doing it. You can do continuous time, where the clock only moves forward when something actually happens, and you can jump forward large gaps if nothing interesting is going on. There's lots of ways of doing that, but we've chosen discrete time, largely because it's simple, it's easy to think about. It's sometimes computationally demanding, so that's a trade-off that we've made. So here's how I represent one of these things in code. So now we're starting to look at how you would actually write a model in Vivarium. So this is the fragment of my vegetative growth model. So we're looking at a piece of this guy now. which is going to determine how big my plants get over the course of growing season. And you don't need to understand all of this right now. I'm going to talk through some pieces. So this is a event handler for a time step. So every time this loop ticks, this guy's going to get called, along with every other part of our model that is time dependent. And it's going to do something. It's going to do some calculation. And in this case, what it's going to do is it's going to figure out how fast it should grow, and we'll talk about where that information comes from in a second. And then it's going to just add, I grow 2 inches today, or a quarter of an inch today, to the plant height, and then write that back to the state table, and I'll talk about those in a second. But this is the important part. It's an event handler. If you guys have done event-driven programming before, you'll be very familiar with this. And so the framework just has a bunch of these time step event handlers registered with it, and every time a time step happens, it calls them. And that's an important way of structuring models for this kind of encapsulation that we've got. And that's how Vivarium approaches it. So the next core thing that is important for understanding how we approach models is what an individual in our individual-based model. In microsimulations, we're talking about individual plants, individual people. If you've done this kind of modeling in the past with other frameworks, you may be used to seeing a person represented as like an object, a Python object that has attributes on it that gets methods called or something. That's not how we think about it. We think about these things are our conceptual groups. So what I'm describing here is a behavior of the individual, not an attribute of the individual. That makes sense. This is I'm talking about how they grow, how they age, how they get sick. And so that lets me, because we're slicing by behaviors, not by behaviors across the population, not by individual attributes. That lets me do this, which is how we represent the individuals in the population. So this looks like a spreadsheet or a database. If you guys have done work with those things, which I'm sure you have. In practice, it's a pandas table. Pandas data frames are the primitive that we use for talking about this kind of data. And this is the state of our system at a given time for 3 plants. They have primary keys, and that'll be familiar from databases if you've done work with that. And so each row represents an individual plant. Each column represents an attribute that plant can have. So plants are a particular size. They're a particular place in their life cycle. They've grown a certain amount of potatoes, like tuber weight. They're in a particular location, and they have some level of infestation with a pest that we're going to model. So this is okay. This is sort of how these relate to the groups that I showed earlier. The columns are the responsibility of particular submodels, right? So my placement model is responsible for the location of the plants. My beetle model is responsible for the infestation level. My growth model is responsible for the actual growth of the plant. And then the Vivarium framework itself tracks the metadata, the things. And when we talk about these things, we access the state table, the underlying state of the system in a way that is very carefully controlled. So when I'm going to use one of those columns in my state table, I need to tell the simulation that that's what I'm going to do. And this, again, it helps us keep our individual models carefully encapsulated so that we can know exactly what data each model is using and how they relate to each other. And I do that by, like I declared a thing as a event listener before, I say that it has data needs. In this case, this is the way in which I declare one of these columns. So it needs the tuber weight, so this column, and an event listener for my initialization events. So this is an event that goes out in the system when a new member of the population is created. So this is at the beginning of the simulation if you have a cohort, a fixed population coming in. If you have a model with fertility, like new plants are born or new people are born, these events get handled every time a new person enters the simulation. And then, because I've declared that I access data, I have a view into the underlying state table. We call them population views, which I can write to. So I'm going to write to my population view and say that everyone starts with a tuber weight of 0. If you're not familiar with pandas, PD is the standard abbreviation for pandas, just like NP is for NumPy. And series is an array. It's a list of values. So I'm saying, give me an array of zeros that are indexed in a way that's aligned with my event index. And the event indexes are how we express what population is affected by a given event. So I'm saying the event index for this initialization event is the people who were born, or the plants that were planted in this time step. And so I'm saying all of those people should start with a tuber weight of 0. And that makes me the initial value of this column, right? So that's how we express the structure of our data. So every model will have something like this that makes the columns that it's responsible for. And then something like this is my time step event listener that transforms those columns over time and tells us how the simulation progresses. So just to remind you what we're building out here, we've talked about how each of these guys establishes its schema, basically what data it's responsible for within the state of the whole system. And we've seen at least a sketch of how those states are going to be recalculated over time as the simulation progresses. Now we're going to talk about these red arrows, which are slightly mysterious, which is how these things represent each other. So in this casual notation, I'm saying that the size of a plant, how much it's grown, affects the rate at which it will produce tubers. So a big plant is going to grow potatoes faster than a small plant, which is true if you're familiar with plants or with potatoes. Also, the plant goes through a distinct life cycle. It doesn't actually start forming tubers until fairly late in its life. And so there's going to be a point at which it reaches a level of maturity which it can make potatoes. That also affects the tuber growth. It's effectively 0 before then. At that point, it becomes non-zero. And then it goes back to being 0 when the plant starts to die, when it senesces. So that's what these arrows represent. I'm saying something about this affects this rate. Something about this affects this rate. Similarly, beetle infestation slows down growth. And since I'm modeling beetles as an infectious disease, effectively, they jump from plant to plant. The density of the plants, the location of the plants affects beetle growth. So I've got all of these sort of causal arrows, right? And so now we're going to talk about how those work. So if you just have a single value, and this is, say, the rate of plant growth, and it might be a single rate if you've got a really simple model like what I'm doing. It might be a rate that varies over time and location and age and sex if you're looking at data for a population. So that's, in the population health stuff we do, that's typically how our things look, is like we know the rate of a disease for, men between 40 and 45 in the United States in the year 1995, right? We would have a value for that. And this would represent that whole table of values over all time, all sexes, and all ages. And so I could build that into each of my things. I could have, there's a growth rate, and it would just be a single value. And then, every time step, I would grow the plants by that value. But that doesn't give me the arrows. It doesn't give me the communication. So I need some way of turning this into a thing that I can influence with other values. And the way we do that is we split it. There's an input, so this is our background rate. So this is like, if the plant were totally healthy and fully grown, it would be growing at this particular value. And then in the simulation, when I need to know the rate at which it's actually growing, I can query the framework and say, what's the current value of this? And if there's nothing interesting going on, if all of my plants are full grown and they're all healthy, I'll just get this value back out. But in practice, that's not the case. Like, there's always something in the middle. So like, one of my plants is small and the other ones are big. You know, one of them's infested and the other ones aren't. And so I need something that hangs out between these two things and can modify it. And again, we're trying to keep with modularity and encapsulation. So I want to think about those as something I can drop into the simulation. And these guys don't necessarily have to know what's in the middle, or the code that a normal user would write doesn't have to know about what's in the middle. The framework should take care of organizing the stack for me and making sure that its effect on the value is applied correctly. And the way we do that is by giving this pair a unique name. So I say like, potato tuber growth is what I might call this. The system will register potato tuber growth at the beginning, assign it a base value, and then anything that wants to affect potato tuber growth that comes into the simulation later is, you can think of these as plugins. Our components are like plugins. We'll say, I'm going to modify potato tuber growth. And this is what that looks like. So I'm modeling this arrow. This is code snipped out of what's at that repository I showed at the beginning. And so I have up top, I say this function, if you need to know what the base value of potato tuber growth is, this function is what you should call. And it knows that there's a growth rate of 1.8 ounces a day, which is a value that I very crudely calibrated to produce approximately the right potato weights at the end. And if, and I'm not going to go through some of the details of this, but if for every plant that is currently in the tuber growth state, it will grow by that much. Other ones will grow by 0. So that's what my base rate is. So that's how I'm thinking about the relationship between the life cycle phase of the plant and this growth rate. And then I have this guy where that value is used. And so I've defined this variable or this attribute on the object to be my potato daily tuber growth value. And I'm saying, for my current population, remember event.index is the population that we're currently thinking about, calculate my daily growth. And so, again, if nothing else is going on, I'll get 1.8 for the people who are currently in the tuber growth phase of their life cycle and 0 for everybody else. But I've got another model. This is my model of plant size, vegetative growth, which has said that it will modify this value. The other guy produces it. This one modifies it. And it's going to modify it based on a thing in my state table, which is the size of the plant height. And what that's going to do is it's going to say full growth potential is reached at 24 inches, because that's about how high a small potato plant gets when it's full grown. If you're less than that, you're growing at some fraction of full growth. And so I just give that as a multiplier to my rate. So if I'm 4 feet tall, I'm a huge potato plant, I'm going to grow twice as fast. I'm going to grow tubers twice as fast. If I'm a tiny little potato plant with hardly any leaves at all, I'm going to grow at a tiny fraction of my size. And so that's what this says. So, if you look at these things, the thing at the beginning, the things in the middle, and the things at the end, we've got those represented as code. And the thing that's important here in terms of the structure of these, or the organization of this modeling framework, is that the thing at the beginning and the thing at the end don't have to know anything about this. It could be there, it could not be there, there could be 10 different things, so long as they have some mathematical properties, like they're all multiplicative, then they all get applied correctly. and you get an effective daily rate at the end that takes into account everything you're modeling. And that's super nice, because that means that I can say, you know, if I want to run a simulation in which I'm assuming all of my plants have a particular size because I have some empirical data where that's true, and I just want to see what happens over the course of the month and a half where they're forming tubers, I can just do away with the growth model entirely, start with fixed sizes for my plants, and run that forward. And I don't have to change any of the code around it. I just pull this model out, which is super convenient. Okay. When am I done? 10 minutes? Okay, cool. Okay, so I'm going to go through the rest of this pretty quickly. There's one more important thing, which some of you will probably recognize. We've got state machines. Not everything is state. Some things are these continuous variables like plant size. But a lot of things in mini models are state. So you can be alive or dead, sick or healthy. In this case, you can be just emerging from the soil, in your main growth phase, forming tubers or dying. And so we have a way of representing these state machines that is works nicely with the rest of our tools. I've simplified this a little bit so we can have them all up on the screen at once, but what I do basically is I define each of my states, and they have names. In this case, they also have a vegetative growth value. So like while the plant's still emerging, I say that it's growing at a rate of 0 because it hasn't actually hit the top of the soil yet. In its main growth phase, it's growing at its full potential. In the tuber formation growth phase, it's still growing a little bit, 10% of its potential. And then when it starts dying, it stops growing completely. So I make those states. So I've defined these bubbles with those 3 lines at the top. The 3 lines below it, I'm defining these transitions, these boxes. So I'm saying that there is a rate at which plants who are currently in the emergence phase will transform into being in the main growth phase. And every time step, I go and I check that rate. And I convert it into a probability at which that transition will happen now. And anyone who transitions just bumps forward into this next state. And any effects that are associated with that state, like more growth, come into effect at that point. And from that point forward in the simulation, those will be happening. So, you know, earlier when I was showing the black dots, like that's what moves the black dots around is these rates. Lots of ways of thinking about that. Exponential probability, which is the rates, is how most of our models work. You don't have to think about it that way, but it's when you're thinking about things in time, that's real convenient. But the framework lets you talk about probability. So you have some other way of calculating an event probability in a particular time. You can do that as well. Rates are just often what you want. So I'm going to go through this quickly. We've already seen several pieces of this code already. This is a full component. It's a very simple one. This is my model of vegetative growth. And it's got, you know, the part where it sets up, it's a life cycle phase where it's registering all of its important bits with the framework. And this is where it says, I'm interested in this value, daily vegetative growth. And I have a function that is the source of that. Typically, things will be much more complicated than a fixed rate. But for this, I'm just using a fixed rate. So this is the source of that value. I'm going to use it later. I set up my schema in the state table. And then I have growth over time where I get my rate added in. Saw that earlier. Here I have this guy. He consumes vegetative growth, but he modifies tuber growth. Because I want to say if the plant is bigger, the tubers grow faster, right? And so that's where this happens. And we saw that code earlier. And then at the end of the simulation, this is a really ad hoc way of printing out results. Normally I would write them to an HDF file or something else. But just for the convenience here, I'm going to print out how large my average plants are. And I just get those by querying the state table. It's got all the data in it. This is the planting components. I'm not going to talk about it in detail. It just distributes guys randomly over the ground. So this is the kind of results that you might get out of a model like this. I lost a slide. Okay. I was going to show you there's a configuration file that tells the framework how to assemble all these models together. It's just a YAML file where I say, I want the planting component and the growing component and the vegetative growth component all together, and then here's the time at which I want you to run it over and how long I want the time steps to be. So it's just a configuration file. They're not very interesting, but they're important to defining models. Because often, if you're working with like a researcher, that's what they're writing, is they're plugging together the building blocks of the model and then putting some parameters into it. So this is the kind of results you'd expect, and this sort of makes sense. If my plants are real dense, this is 1 plant per square foot, which is much denser than you would ever plant potatoes, and I have a density-dependent disease like flea beetle infection, I get lower yield, just a couple of pounds per potato or a few pounds per potato. If I make them sparser, I get a higher yield, but there's a diminishing return there. So, face validity seems okay. That's about the shape you'd expect. Obviously I made up all this data, so don't plan your garden this way, but it's about right. This is a more complete result, more like what our model actually outputs. This is a cardiovascular disease model. This is preliminary results for Ethiopia. And we're studying the cost effectiveness of different ways of treating people with high blood pressure and the effect that has on cardiovascular disease. So this has been run tens of thousands of times to sample the full distribution of the results of the model, because there's stochastic variance in it. These are random models. And this is one way you might look at the results. So I'm going to leave that up because I like colorful dots. That is the end. I think I have, like 5 minutes left? So I'll leave that for questions. If you're super interested in this, there's a couple of things you should do. Jacob is giving a talk later on similar subjects, scientific modeling. You should go see that tomorrow. Also, if you're really interested in this, sounds awesome. My group is hiring. If you want to move to Seattle where it's cold and rainy for the next 9 months, you can search for IHME careers or come talk to me. And that's it. If anyone has questions, I'm happy to answer.
Let's give Alec a round. So I'm really interested in simulation, but I'm brand new to it and stuff.
Okay.
Is there a, but the area that I'm interested in is areas where the model is not well defined.
Sure.
I don't have a really good mathematical idea of how things are going. I'm going to take guesses.
Sure,
right?
sure.
And stuff, and I want to be able to, based off of how I see things over time, determine, have to give hints basically as to, where I can go look for maybe adjusting my model and getting more data. So are there pieces of Vivarium that help in doing that?
So the process you're describing is called calibration, right? So this is where I have some idea of what my model looks like. Maybe I have a general idea of what the structure is, or a very detailed idea of what the structure is, but I don't know what all the parameters are going to be, right? And I can calibrate the model by running the model, varying the parameters, maybe even the structure, and looking at how well it predicts actual results, right? And tweaking things based on that. So it's an optimization problem. And this is a very common thing that modelers do. My group sits on top of a data set that we get to treat as ground truth. So we actually don't do a lot of calibration. So Vivarium itself doesn't have tools for this built in. Eventually we will, because we have implicit parameters, and we'll have parameters that we need to tune later, certainly. There are a lot of approaches to that. Unfortunately, I don't know that much about calibration, because I'm actually fairly new to this still. But if you just search for that, if you search for model calibration, there's a lot of good approaches, and people have done a lot of research on that.
So I have a potato-related question.
Sure.
What kind of interventions would you look at to figure out what should I actually do to help my potato grow best? Because I actually have a potato home at home right now that I'm trying to grow this.
Nice. Okay. So do I. Yeah. So for density-related things like flea beetles, which are super cute because I love teeny beetles, but they're terrible. You want the spacing of the plants to be right, and then it's often useful to have other plants around. So if you have problems with flea beetles in particular, planting radishes is great because they super love radishes and they're just okay about potatoes. So if you plant a radish, they will eat that radish and they will leave your potatoes alone. So if you were trying to use, say, a model like this to study that, you can do a graph like I have of hey, somewhere in here there's a sweet point of my actual total yield, because as density decreases, my total yield goes down, but my yield per plant goes up, right? So somewhere in here there's a sweet spot, and you could look for it. You can also look at the effects of spraying. Do I want to spray pesticide on one plant? Only strongly infested plants, other plants. You can study things like that. In practice, I think companion crops are the way to go for flea beetles in particular, and spacing is good for a lot of things. And
Can I follow up?
Yeah.
Like, do you have to model an entirely separate population for radishes, or do you kind of like have a stand-in that's just like this is what we think of you?
Right. So Vivarium right now makes some assumptions that there is a homogeneous agent population, so a single type of agent, just potatoes. We are going to release that restriction pretty soon and look at multi-agent type models, because often that's what you want. So like here you might want radishes and potatoes. Maybe the beetles are also an agent in your system. Like you could talk about it that way. In the public health world, you might want like healthcare consumers and healthcare providers as separate agents, because it might matter, whether or not the doctor is at the clinic at a particular time, right? So there's lots of cases in which you do that kind of modeling. Vivarium doesn't have support for that. It's easy for us to add in, and we will eventually as soon as we have a use case, because right now all of our development is driven by the internal needs of the institute. So, yeah. Oh, thank you.
So follow up kind of on your answer to his question. How do you mentioned that this is good for like a homogeneous population? How does that come into play when you're actually looking at certain diseases that have impacts across many different types of people?
So, okay, that's a really good question. So when I say homogeneous, I mean people. If I were trying to study like zoonotic diseases where I want, say, people and camels, we have some trouble with that. But if I want like young people and old people, or men and women, or different like ethnic groups or something, places where mixing like that is important, as often is in diseases, we do support that. So when I was talking, I'm not going to go back. When I was talking about the values, where I have just like a fixed rate of growth, often what that actually is it's a table. So I know what the rate is for men who are of a particular age in a particular place, and I know that it's a different rate for women of that age in that place, or men in a different place, or women in a different place, right? So I can have population heterogeneity that way that's controlled by my input values, and often that's what you look at in sort of disease modeling. So, Jacob?
So I'm familiar with this work, so
Sure,
my
yeah.
question is actually aimed at this, because there's some things you didn't mention here.
Okay.
If someone's going to start now looking at some sort of microsimulation tools,
Sure.
tell them why to use your tools, and tell them what will be in the future. Why is your tools better? And
Okay.
It's better in some cases, and what are you planning for the future for this?
Okay.
And do it in 1 minute.
1 minute. Okay, I'll be real fast. So the trick to this question is he has also developed a very similar tool called MIST that does similar kinds of modeling. So we are great because I think one of our core things is this idea of encapsulation and decoupling. Like we do that pretty well. I think in a lot of ways we do it better than most other models out there. We're also based on modern Python tooling, which a lot of older models are not. We have another thing which I didn't talk about here because it's complicated to explain, called common random numbers, which we have very good support for, which is a way of reducing variance in these kinds of things. So if I want to run interventions here where I've got counterfactuals, like a world in which I supply a certain drug versus a different drug, I'm not going to talk about the details, but that becomes very, very tricky to do in stochastic models like this. Common random numbers is a way of doing it that doesn't require huge amounts of computational time. If anyone has curiosity about that kind of variance reduction, I'm happy to talk about it. But I think those things, encapsulation, variance reduction, and just we sit on top of a modern tool stack and are under active development. There's other people you could say that about too, but I think those are the ones that are important for us.
You're fast.
We're relatively fast. We're not as fast as we could be, but we're fast, and we're getting faster. And we're designed to run on large clusters. That's another thing. Vivarium doesn't provide a lot of direct support for that, but it is easy to package Vivarium and distribute it out across a large high-performance computing cluster and do work that way. Something like this, which is many tens of thousands of CPU hours to produce these results.
That's good.
So MIST says use Vivarium, it says
Actually, there are some differences as well. But
Let's give Alec one last round of applause.